Welcome back to Epistem, and in today's video we are going to talk about the disaccharides. This is the part 2 of our carbohydrate series, and in the first part we talked about monosaccharides. So let's get started. So disaccharides, they are formed when two monosaccharides are joined covalently by the O-glycosidic bond, which is formed between the hydroxyl group of one sugar and the anomeric carbon of another sugar. Now here in this picture we see two glucose. Now in the first one we have this carbon number 1 as the anomeric carbon, and in the formation of maltose this 2 glucose will be contributing. So for the first glucose, this anomeric carbon attached to that is the OH group, which is actually taking part in this reaction. So for understanding this reaction of the two monosaccharides forming this maltose, we need to consider this reaction first. So this glucose, it's actually a hemiacetal. Now why is that? Because if we consider this structure and match with this one, so this is the central carbon and we have a OH here and one H is also attached, which is like not shown here, but you have to imagine it. Next we have the R1. R1 is this one from the bottom. So from carbon number 1, this part is the R1. And next we have OR2. OR2 is this one. This O and R2 is the rest of the part. So it's a hemiacetal. Now here the second glucose, it's carbon number 4 having this OH group. This OH group will take part in the reaction. And to understand this, again we need to consider this reaction. So what happens is that this hemiacetal, it has this OH. That means this OH. So this OH gets replaced by the R2O. R2O, it means this O and this part, this R2O. So this OH will get replaced by this part and the H will be left behind, which will add up with this OH and the water will be formed. So this water is formed. Now these reactions I have already discussed in the first part of the carbohydrate series in the monosaccharides, and to understand this part very clearly you can go and watch that video and then come back here. So the glycosidic linkage is formed between these two monosaccharides, and now this structure is an acetal. So again we can match it with this structure to prove that. So this center is the anomeric carbon. So this is the sugar that is contributing the anomeric carbon. So that's why we are considering this anomeric carbon and not this one, because this anomeric carbon of the second sugar is not contributing in this reaction. So this is the central carbon, and with that we have a H attached. Now this H is not shown here, as I told, you have to imagine it. And one is the R group, R1. So R1 is this part from the bottom, and OR2, this yellow one was already present. That means OR2 means this one, this O and R2. This is the yellow one. So remember this color demarcations, because it will help you to understand that which one is contributing and which is the part of a second sugar and like that. So the red OR2, this is the second sugar. So this is O and R2, this part. So this red OR2 is this one. Don't confuse between these two. So this is how alpha maltose is formed. Next we will talk about disaccharides to monosaccharide conversion. So this conversion is actually done by boiling the disaccharide with dilute acid, and the bonds get hydrolyzed and we get the monosaccharides. It's very simple. The next topic is reducing sugar. So we just talked that in maltose, the second sugar that is contributing in the reaction, its anomeric end, its anomeric carbon, it is not contributing in the reaction because the carbon number 4 and the carbon number 1 of this first sugar is contributing. So as a result, the anomeric carbon of the second sugar is free, and this end is called the reducing end. Now, reducing end, what does that mean? So in aqueous solution, this reducing end, it gets converted to the aldehyde group, and this aldehyde group undergoes oxidation to form the carboxylic acid. And in this process of this conversion, the reagents that are present, like the tolerance reagent, they get reduced. Now, since this reduction is done by the anomeric end of these disaccharides, so they are called the anomeric, so they are called the reducing end, and these are reducing sugars because these sugars can reduce the reagents. Similarly, we have the non-reducing sugar, which is the opposite of reducing sugar. Here both the anomeric carbons, they are contributing in the formation of the disaccharide, like the sucrose and trehalose. Here see the carbon number 1 here and this one, and here also the carbon number 1 and this carbon number 1, both of them are contributing in the formation of the glycosidic bond, and none of them have the free anomeric carbon. So as a result, the reduction of tolerance reagent is not possible, and so they are non-reducing sugar. Now we will learn how to name a disaccharide. So again we will consider the example of maltose. So maltose is a common name, and its scientific name is alpha-D-glucopyranosyl 1,4-alpha-D-glucopyranose. Now this big name, now how can we write this? How can we understand that which one to write first and which one to write next? So we consider this structure at first. Now we take the first sugar at first. So the first thing we need to do is to identify if it's a alpha or beta anomer. So now alpha and beta anomer is determined by the location of this OH group of the anomeric carbon attached to the anomeric carbon. So this one is the carbon number 1 and attached to it is this O, and here the direction of the bond shows downwards. That means the OH is at the bottom, and that means that this sugar is having a alpha anomer. So alpha. Then D. Now D, we consider it is a D stereoisomer because the CH2OH is at the top. Next, glucopyranosyl. So glucopyranosyl, because it's a glucose structure and it's a pyranose, 6-membered ring. So that's why glucopyranosyl, and pyranosyl is used, not pyranose, because it's in the ionic form. It's taking part in a reaction. So it's not in a pyranose neutral structure. So it's a ionic structure. That's why it's pyranosyl. And next we are writing the contributing carbon. So here the carbon number 1 and the carbon number 4, they are contributing. So that's why 1 arrow 4. Next we will write the name of the second sugar in the similar way. So first we need to consider if it's alpha or beta anomer. So it's a alpha anomer. It is because the carbon number 1 has the OH group at the bottom, so that's why it's alpha. D because CH2OH is at the top, and glucopyranose because it's a glucose structure and it's a pyranose. Now we will see the examples of lactose, sucrose and trehalose and understand the nomenclature from a better perspective. So first one is lactose. So in lactose we have the first one. We will consider the first sugar, which is in a beta anomer state, because the first carbon we have the OH at the top. The bond, you can see it is present at the top, so that's why it is beta. And then D, because the CH2OH is at the top, and then galactopyranosyl, because it's a galactose structure. Galactose, why? Because at carbon number 4 the OH is at the top, and in glucose what we had? In glucose we had this OH at the bottom at carbon number 4, so that's why it's a galactopyranosyl. Pyranosyl because it's a pyranose structure and it's in a ionic form, so that's why pyranosyl. 1,4 because the contributing carbons are 1 and 4. And the next one is the second sugar, so here the beta D glucopyranose. Now beta, why? Because beta, this is the carbon number 1 and the OH is at the top, it means it is beta. D because CH2OH is there, and glucopyranose. Now gluco, why? Because at carbon number 4 the OH is at the bottom. So we just saw that in galactose the OH at the top, or at carbon number 4. So it's a glucopyranose. Next we have sucrose, and here what we can see, it's actually sometimes we can also write the scientific names from in an alphabetical point of view. So like fructo is like F comes before G, so that's why sometimes we prefer writing the alphabetical names in alphabetical order. So here this one is written first, but both the procedures are correct if we consider this one first or this one. But since it is written here from this perspective of alphabetical order, so let's consider this one. So it is beta D fructofuranosyl. So why is that? Now the anomeric carbon, this is beta. Now why is that? Because you see this OH is directing in a downward direction, but still we are calling it beta. It is because when we start counting in an anti-clockwise direction, see 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6. So this is in a anti-clockwise direction, and when the counting is in anti-clockwise direction, the anomers get reversed. Like it looks like it's supposed to be alpha, but actually it's beta because the counting is in a anti-clockwise direction. And so it is a fructose structure, so fructo and furanosyl because it resembles furanose. And then we have this 2 and 1, so the contributing carbons are 2 and 1. The next is alpha D glucopyranoside. So here see again the direction of this OH group is at the bottom, and here we are calling it alpha. It is because you see the counting is in a clockwise direction, so 1, 2, 3, 4, 5 and 6, so it's in a clockwise direction, and as a result the anomers are as it is, like what we have learned, that if it is at the bottom it is alpha. So here it is alpha D because the CH2 which is at the top, and glucopyranoside. So this is the scientific name for the sucrose. So remember this part. This part is very confusing sometimes when we see the structure of this fructose. Like here the direction of the OH is at the bottom, but still we are calling it beta. Why is that? It is because the counting of these carbons is in a anti-clockwise direction. Next we have trehalose. So in trehalose the sugars are this alpha D glucopyranosyl and alpha D glucopyranoside. So here the alpha because this is the carbon number 1 and the OH is directing at the bottom, so that's why alpha. D because it is CH2OH at the top, and glucopyranosyl because it's a glucose structure and it resembles like a pyranose. So Then we have the 1 and 1, that means the carbon number 1 and this carbon number 1 are contributing in the formation of this glycosidic bond. And in the similar way, we can name this second sugar. Now we will talk about invert sugar. So sucrose, it is also called invert sugar. Now it is because when sucrose it is present in this format, it is actually dextrorotatory. That means it rotates the plane polarized light in the right direction. But when we hydrolyze this sucrose in its contributing monosaccharides, that is D-glucose and D-fructose, then the individual property of this glucose is that they are dextrorotatory, and fructose they are levorotatory. So that's why it is given as negative. So that means it will rotate the plane polarized light in a left directions. So here if we consider the net degree in net change in degree, so that is like minus 39 degree, which is levorotatory. So that's why when we have sucrose as it is, so it is dextrorotatory, but when we hydrolyze this sucrose, we will get the solution whose optical rotation is levorotatory. So that's why it is called the invert sugar. Now here are examples of some oligosaccharides. Now the disaccharide is also a part of oligosaccharide. So when we consider oligosaccharide, so it means that more than one contributing monosaccharides are present in the compound. So disaccharides we just talked, and these are some examples where more than 2 monosaccharides are contributing. Like raffinose, we have 3 contributing monosaccharides. In nistose, we have 4. So like this. So these are the examples, you can read it. So that's it for the disaccharides. Thank you for watching and subscribe for more updates.